Hello there. This video is more or less a talk through this Jupyter notebook that I put in the KLE on the topic concerning kinematics. So the idea of this is to take a position vector and try to use this to trace a trajectory out in Python. And this you might find useful in assessments. What we need to do first off is, of course, use plot commands, and we know that first of all from previous videos that matplot library is an important thing to use, so that's what that line is doing. And this must be executed before you use the worksheet in full. There is also the numerical Python module, which has been called here, and this is because a lot of the calculations will involve, again, some numerical computation or number crunching. There is an ability in this worksheet to have animations. My suggestion is, well, if you want to wait a bit of time and see what this animation produces, this will save to your computer in the library, I think, either on the desktop, or it might save also if you're using the Jupyter Hub to the library inside the Keil Jupyter Hub. But in any case, this will simply add a point that follows a curve which is traced by this position vector, which describes the point moving along this curve. Now, how does it work? Well, this thing depends on t. I have now another way of defining a range variable is like this. So you can use a range. You can specify the initial point and the final point, and then you specify the step. So you can make this as fine as you want, but be careful. It is, well, the finer you make it, the longer your computations are going to get. So let me just run this at the top. Let me just go to here. Next, what am I doing? Well, I know this coefficient of I is x, this coefficient of y j is y, and this coefficient of k is z. So what I do is I will add in the functions now, define x as a function of my range variable t, which represents time. And the way it works is like this. It's quite simple, actually. I can define x, this x component, as follows. I just take the expression for x as a function of t and type this in this way. Okay, so here t is a vector or a range variable. It has a large number of entries, but what it does is it does a sort of clever calculation that Python understands that it's adding vectors together. You might ask, well, what the hell is the cosine of a vector or a matrix? Well, this is how it operates in a clever way. These packages, these software tools, it actually takes the cosine of individual elements in the array t. So it will do 3t plus cos of t, and that will give me my vector x. Again, x is a vector and that will correspond to all those values t inside this vector t. Again, I'm doing the same for y down here. So, oh, it's gone crazy again. I think it's just because I click on, hang on, some stuff as it's recording. So for y, yeah, it's the same. So my y component is 3 plus sine t. You can put anything you like here. Maybe you're given some particular position vector. You can define x, y, and z anyway in this way. So after this, I'm also defining a zeros vector. Why? Because the coefficient of my basis vector k is 0. So what I would like is for each value of t, my z component to be 0. So this actually sets up a vector of zeros, and the vector of zeros is determined by this len of t. What is len of t? The length of t. Okay, so remember that this t is a vector. In this case, it's a vector of all time steps taken, all times taken with which you perform the computation. So I'm going to execute this line. Good, they're in the memory. Now I'm coming down to adding in the plots. Now what I've done in the KLE version of this file is I've added in commands that allow you to make animations well, you do with this what you like. You might be sat there sometime. It's quite nice to look at, especially if you're doing very complex trajectories traced by your position vector. But in this video, I'm just going to show you how to plot this. So this is the command now. Command lines. I'm doing a 3D plot of this. And what I am trying to do is plot X, Y, and Z in here. Okay, so these are the vectors X, Y, and Z set up earlier using this command, which is line equals x.plot X, Y, Z and label parametric curve. Okay, so it plots the parametric curve followed by R, or the particle, as t evolves in time. Or as you would say, as t runs on. Additionally, I put a point on, that's this line, which represents the initial value of x, y, and z, which is the 0th component. Remember, x, y, and z are vectors. The first component is always labeled 0. And then this command has added a legend. What is that? Well, on this diagram, that is just the legend. The orange line it's telling you is the parametric curve. Okay, so this is the colon sequence. Now, if I were you, I would just keep it as it is. There's nothing really to change here. The only thing you need to change up at the top is the x, y, and z functions. And yeah, so if you shift and enter, that's what that does. You can also rotate the plot in this worksheet by using the following commands. So you can set the limits for x and y, okay, and you can set the limits for also the azimuthal limit and elevation, which determines the pitch at which you look at this plot. This is a 3D plot. You're looking at this from a particular angle. And so you can determine, or you can tell Python, well, I would like to look at this at just the XY plane, and that's all I've done, bird's eye view of this curve, and there you go, and set the limits appropriately so that my curve touches the top and the bottom of this. So you can do many things just by playing with these. These commands are the same as above, and this. The only difference is I'm playing with the axes limits and the angle from which this 3D plot is viewed. So have a go in labs at using this. You might find it's very useful in answering particular questions and visualizing certain position vectors. Okay, good luck.